So if that's true, then we can use the same logic to convert from entire radicals into mixed radicals. The way that we do that is there's two possibilities that we can use. One is we can use a prime factorization method, which a lot of people find popular because it's pretty simple and pretty straightforward. The other would be factoring out perfect squares. Now, the catch is when you're factoring out perfect squares or perfect cubes or perfect fourths, you need to know what they are. And ideally, you need to know what the biggest one you can divide it by is, which you might not always know. So if we factor out the perfect squares, then I could say, well, the square root of 72 is divisible by 4, which is a perfect square. It's divisible by 9, which is a perfect square. Or it's divisible by an even bigger one, which is 36. And I would split it into 36 and 2. And the square root of 36 is going to be 6. So I can say that that's going to be 6 root 2. Now, if you didn't know what the perfect squares were or how to factor them down, you can always use a factoring tree. Take the radicand, 72, and you're going to factor it down. So I divide by 2 to get 36, keep dividing by 2, keep dividing by 2 until I can't anymore, and then move to the next prime number, 3 and 3. And then what I'm going to do is I'm going to circle the sets of 2 of the same prime number, because if we're taking square root, we're looking for 2 of the same prime number. If I have a set of 2 of the same prime number, then I can square root the 2 times 2 and get one of those outside the radical. I can square root the 3 times 3 and get one of those outside the radical. And anything that doesn't have a pair of the exact same has to stay inside the radical. And then at the end, all I do is I multiply together whatever is outside the radical, I multiply together whatever is inside the radical, and I'm going to get the answer 6 root 2. So I will admit, if you can do it this way, it's faster. But if it's bigger numbers or you're having issues, this method will always work as well. If I have an index of 3, that just means that I need perfect cubes. So if I take 108, the nice thing is there's actually only one perfect cube you can divide out of there, which is 27. And I get 27 and 4. Well, the cube root of 27 is 3, which means that I can make sure that it's going to be 3 and the cube root of 4. Please, please, please don't forget to rate the index at the end here. It is amazing how many people will lose marks or get it wrong because they always just write the square root symbol or just the radical symbol. They will forget to actually write what the index is at the end. Now, I can use the same process that we did in the last case, in case you're not sure what the perfect cubes are, in order to factor this down. I can take the radicand, 108. I'm going to divide that by 2 and get 54. I'm going to divide that by 2 and get 27. Can't divide by 2 anymore, so I divide by 3 and get 9. And then 3 and get 3. In this case, because the index is 3, I need 3 of the same number in order for one of them to make it out. And then anything that does not have 3 of the same number has to stay inside. So there's a 2 and another 2. And I get the exact same answer, 3, and the cube root of 2 times 2 is 4. So if I'm using this to convert these radicals into simplest mixed form. Simplest mixed form just means the radicand no longer has a factor that is a perfect square, a perfect cube, or perfect fourth, whatever the index happens to be. So if I take the square root of 320, the biggest perfect square I can pull out of there is 64, and I'm left with 5. Square root of 64 is 8, root 5. When I take the cube root of 6,000, then that's going to wind up being the cube root of 1,000, biggest perfect cube that I can pull out of there, and the cube root of 6, or 10, and the cube root of 6. When I get to the fifth root of 486, this is one where you'd probably like to use a factoring tree. Most of you probably don't know what the perfect fifths are. But if you do, you can pull it out. And you're going to get the fifth root of 243, or 3 times 3 times 3 times 3 times 3. And I'm left with a 2, or the fifth root of 2. So 3, the fifth root of 2. When I get to the last example here, I can see there's a negative in there, but it is a odd index, which is okay. It just means I'm going to pull the negative out when I'm simplifying this. So I already have a 2 on the outside. I'm going to remove the perfect cube of 8. But I'm also going to pull the negative out of there. And left with the cube root of 5. This is the same as 2, and cube root of 8 is negative 2. And the cube root of 5, and 2 times negative 2, negative 4, and the cube root of 5. We don't need to know the distance formula, so don't worry about that part. You do need to know how to convert mixed radicals into entire radicals. So the simplest way is, if I pulled it out, I need the same number of them that matches what the index is, which means to move them back in, I'm going to do the exact same thing. If this has an index of 2, then to move it inside of a radical, I would need to have 2 of them again, which is the same as 9 times 7, or the square root of 63. If it has an index of 3, then I would need 3 of them, 3 of the same number to pull it out of the radical, so I'd need to have 3 of the same to put it back in the radical. So I can just say that it's going to be 1/2 times 1/2 times 1/2. 3 of them to get back in there. 1/2 times 1/2 times 1/2 is 1/8. And 1/8 times 160 should be the same as the cube root of 20. So if I'm converting these into entire radicals, then I'm going to say for the first one is a square root, so the square root of 2 times 2 times 3, or the square root of 12. For the second one, it's a square root, so I can't move the negative in, but I still need to state that it's negative. So negative 5 times 5 times 6, which is negative square root of 150. Don't forget the negative here, otherwise it's wrong. The next one is a cube root, so I can move the negative in. So I'm going to say that this would be equivalent to the cube root of -4 times -4 times -4 times 6, or -4 cubed times 6. Same logic works. And that's going to be the same as the cube root of -384. When I get to example D, if it's a fourth root, then I'm going to take the fourth root of 5 times 5 times 5 times 5, or 5 to the power 4 times 2. And this is going to give me the fourth root of 1250. And the last one works the same way when we're doing it with fractions. This would be the same as the cube root of 4/5 times 4/5 times 4/5 times 100, which is the cube root of, when I reduce the fraction down, 256 over 5. If it wants us to arrange mixed radicals in order from least to greatest, if we need to see them without dealing with the decimals, then it's a fancy way of saying put them all into entire radicals and you can see which is bigger and which is smaller. So when I take 3√6 and I want to turn it into an entire radical, it's the same as the square root of 3 times 3 times 6, or square root of 54. The next one is going to be 6 times 6 times 3, or the square root of 108. This one does not need to change. Next one is going to be 2 times 2 times 7, or the square root of 28. And finally, 7 times 7 times 2, or the square root of 98. And now I can order them from the greatest to the least. So the biggest one is 6√3, then 7√2, then 3√6, then 2√7, and finally just the square root of 18. All right, that's it for this lesson.